Welcome everyone back to our Data Science Learning Community Book Club, where we are taking on the Generative AI Handbook as outlined by William Brown. Last time we discussed, as you can see in the table of contents on the top left, chapters 1, 2, and 3, and today I'm hoping to walk us through chapters 4, 5, and 6. So that it's not a surprise when we get there, I actually think that the materials in chapter 6 should be mentioned before the materials in chapter 5, and I'll do so as such. We have here in the data science learning community some slides here in the Quarto website format, and let me just take a second to bring up the slides, chapters 4, 6, and 5. Chapter 4 is called Online Learning and Regret Minimization, and it touches upon notions of optimization. Now, as a math major, optimization to me was to take some sort of feasible region in some higher dimensional space, for example, sometimes called a simplex for linear programming, and to find some sort of global minimum if possible. What surprised me here was that, especially when we're looking at this particular resource or textbook, that we are thinking about optimization in kind of a more of a game theory sense, that you have a user who is conducting actions and that you have an adversary who could also conduct actions. And this is outlined here in the beginning of Online Convex Optimization, sometimes called OCO. This book written by Dr. Alad Hazan, and we'll be spending a few minutes here talking about the first chapter. Disclosure, Dr. Hazan is a coworker of mine. To grossly summarize, when we're going through some sort of state space or game or something, there in the first bullet point, we think of player actions based on some sort of strategy, some sort of algorithm. And then the second bullet point, we're thinking of a finite number of turns going from t equals 1 to capital T. What regret is, at least in a theoretical sense, is the difference between the actions and the best possible actions to take. Whether or not you want to call this a loss function or something thereof, you could imagine that our goal here is to somehow minimize the amount of regret over the set of possible actions. As I was implying before, even with this game theory approach, some of the applications of this mindset, users versus adversaries, could be applied to some areas such as spam email filtering, pathfinding in a perhaps video game sense, portfolio selection for stock market investments and such, and recommendation systems. For example, your movie or TV show streamer entertainment output that tries to recommend your next bit of entertainment to you. In the notion of experts and adversaries, if we have some sort of, I believe that's a training rate at epsilon. What I found interesting is that in this framework, if the experts, sorry, I should take a step back. We're picturing a scenario where you, the users, could ask people for advice, maybe just in a binary sense. Should you choose to do something, yes or no? You're going to experts. And these experts could be right or wrong in the grand scheme of things. So the best experts could make maybe say L mistakes over the course of your time. What I found interesting here is that we have developed upper bounds for the number of mistakes that you could make. The first bullet point talks about a deterministic algorithm, and the second bullet point talks about a randomized algorithm. This is useful in the world of statistics and probability because you're always talking about things that could have an element of chance. And when you have an upper bound, you could at least restrict the notion of a worst case scenario. So once again, if you have a few experts that you could ask, literally you could picture yourselves just asking people whether or not to agree or disagree on something, and say the choices were between A and B. At first, your strategy might be to simply choose the majority. Go with choice A if more experts agree with it, or go with choice B otherwise, and that will be your action, lowercase a. Now, especially when we move on to neural nets and whatnot, we have weights towards these choices. And for each iteration t, we can update these weights. We could keep the weight on that choice if the expert was correct, or we could reduce the weight if the expert was wrong. And that's the reduction is done by that 1 minus epsilon factor there. Our goal, of course, is to try to get a balance of when to choose option A or option B. Now, this is still a rather elementary or beginning sense of how to approach this. And if we move on to talking about there in the bottom left, a notion that some decisions might have more loss than others. Some decisions might have more importance than others. So we bring in another parameter on top of the epsilon learning rate. And this time around, you could see that the weight update formula has a negative exponential. So if some decisions are more important, that is, you could get more loss or lose more thereof, the weights will change more rapidly. Conversely, if the decision is not so important, then we don't change the weights as much. As usual, there was probably more mentioned in the chapter in the resources, but at the moment, I felt that this was what I wanted to say in the summary. And like usual, now that we reached the end of a so-called chapter, I'll pause here, see if there are any questions and such in the Zoom chat.
Sorry. I got lost a little bit. Like I don't understand the relationship between this function, the hedging function, and the loss function or the regret function that we saw in the beginning. Are these related at all?
They are kind of related, but it would be like a separation of maybe 2 weeks if we were actually teaching this class. Admittedly, I skipped a lot of details along the way. We're thinking about uh, perhaps better and better algorithms. It's just that the regret function was introduced very early on in an introductory sense.
Okay, but like the regret function, minimizing the regret function, that will be like the kind of like the main goal. No, not minimum.
So yes, in that whenever you want to think about a situation in the optimization sense, whether or not you have a regret function or some other framework, you need some sort of objective. And you want to minimize that objective.
Okay.
Admittedly, I didn't define all these terms. Sometimes we set up these formulas as a theoretical construct because we cannot actually compute everything in here, and then we build an algorithm of things that we can compute.
Okay. Thank you. Thank you.
It seems like the weights of the experts can only decrease but can never increase. What if there was like an expert that was wrong the first time but was correct every subsequent time and infinitely after the first time? Then its weight would never increase, right?
So yes, by the formulas I just happen to have on the slide, that is true, that the weights cannot increase. In general, when you have a network such as a neural network, you would probably want the weights to act like probabilities in that they have to add up to 100%. And when you think about that, you could always, at the end of an iteration, rescale all of the weights so they once again add up to 100%. And in that part of the algorithm, sometimes called a softmax, that's where the increases or decreases would take place as well. All right, so as I mentioned at the beginning of the hour, I kind of found it surprising that the handbook put the so-called Markov models in chapter 6 when I thought it should come a little sooner. So here in the Zoom YouTube presentation, I'd like to go to talk about chapter 6 first, and then we'll go back to chapter 5. In Markov models, I want to discuss a little bit of the mathematical history, namely the Markov property and Markov chain Monte Carlo. Let's get a slightly more concrete example here. Looking up some materials elsewhere, I found this tabular space. It's based on a blog post by Audra Hammerly. And you could picture yourself as an agent walking around these various nodes in this directed network. For example, from the middle node with literally the word A, we have a probability of going to time, sausage, mouse, or bird. And that might have different probabilities rather than being 25% each. With this network kind of in our minds, I want to introduce the notion of a trajectory, walking through that network one node at a time. So example, one trajectory could say once upon a time, a bird and a mouse. Another trajectory might be a sausage entered into a partnership and set. And one more example of a trajectory could be bird, a, and set up house together. So we're thinking of those trajectories as instances of going through this space. And then before I forget, the reason why I'm calling this a tabular state space is because the individual nodes are discrete. They are in some sense separate from each other, as opposed to some sort of continuous function. Uh, I forgot if I mentioned this last time. A stochastic process is a sequence of random variables. From there, the Markov property is that the future of a stochastic process is independent of its past. So here, what we observe for capital X of t plus 1, technically there's a whole sequence of observations before it. But the Markov property says that we only look one step back, or let me say it this way. We only look at the present to guess what happens in the future. We don't need to go multiple steps back. And this assumption is sometimes also called the memoryless property. In the mathematical histories, I believe Markov was developing these notions around the 1890s. So part of the motivation was people did not have handheld calculators, much less personal computers at that time. And it was a assumption to make calculations easier at the moment. But like a lot of things in mathematics, sometimes a formula proves to be very useful and it helps it become something we study more often as history progressed. But once again, what the Markov property is we're looking at the probability of the next step in the future, but only based on one step back right now in the present. As development of the Markov sequences became more in vogue, after World War II, there was a think tank led by Metropolis and that created the Metropolis Hastings algorithm. If you ever heard of a random walk, say if you start on the XY axis and you're just asked whether or not you want to step to the left or step to the right, and you do that with some sort of randomness and hence the name random walk to get a sense of where you can end up. Somewhere in there was a choice of whether or not to stay still or move forward. What the Metropolis Hastings algorithm did was, in a somewhat clever sense, actually give a different probability of whether or not to move. And that's the formula in the middle. This is called the acceptance probability. Do you accept the choice to move to a different spot or do you stay still? In the mathematics of it all, suffice to say, it has something to do with prior and posterior distributions. This Metropolis Hastings algorithm, as simple as it may sound in the grand scheme of things, has been named one of the most important computer programming algorithms of the 20th century by some outlets. Once again, the Metropolis Hastings algorithm obviously credited to those folks there at the top, but there was a few other people working in that lab at the time, and I want to give credit to the person who may have actually created this algorithm, and that was Ariana Rosenblatt. From there, what Markov chain Monte Carlo is there on the left-hand image, suppose we have some sort of uniform distribution. We start somewhere in there. And do I have annotation tools? Perhaps I could use that. We start somewhere there. And we could either move to a new location or we could stay still. And the probability of moving to a new location is lower if you're like far away from the initial distribution in some sense. And we eventually have a trajectory of this sequence. In Bayesian studies, what happens is even in relatively simple problems, we make about 10,000 of these trajectories. And where we end up, we make a distribution, a posterior distribution. Overall, the goal of MCMC is to create a distribution in a situation where the distribution is not obvious, where we might have a complex situation, but we still want to get a grasp of its random variable nature. Now, after about 10,000 chains, getting a posterior distribution, we could do the usual statistics calculations, such as finding an average, finding a variance, and of course, and talking about not a confidence interval, but what's called a credible interval. So those are the concepts I believe are fairly important in this chapter, the Markov property and MCMC. Once again, I'll take a pause here. Any discussion from folks in chat?
I was just looking at the Wikipedia for the Markov chain Monte Carlos and the algorithm, the Metropolis Hastings, and it looks like the entries are good, right? Like they're a good reference.
Yes, and in particular, this particular picture is coming from that Wikipedia article, yes. Have any of you used Bayesian approaches or MCMC in your work?
It's one of the fundamental pillars for building phylogenetic trees and doing genomic sequencing analysis. I think it's kind of widely used Bayesian approaches, how we analyze sequencing, particularly pathogen genomic sequencing. There are different variety of methods, but one of the most foundational is the MCMC approach. So yeah, we'll be familiar with it.
We've used it in algorithms to help impute zeros in high dimensional data sets, like genomic sequencing data sets.
Cool. Yes, thank you both. All right, folks. So like any good seminar, start off with some relatively easy stuff, move into stuff you've heard of. And now in the second half, this is part where I might lose you. So just a warning. We'll move on to, let's see, how do I get out of annotation mode? We'll move on to chapter 5, which was called reinforcement learning. Reinforcement learning, at least for those of us who follow the media, social media, reinforcement learning is the one that's popular for playing video games and such. So we have seen examples in recent years that say Deep Blue plays chess, AlphaGo plays Go. Reinforcement learning has played some other games such as Atari video games and StarCraft and such things. And what I want to do for maybe the next 20 minutes is to try my best to just give an overview of reinforcement learning. In recent years, the popular textbook for reinforcement learning was written by Sutton and Bartow, available for whoever is interested in that. I will fully admit to you, I did not read a 300-page textbook in the past week. So instead, I looked at the videos there that you see on the right, about 2 hours of videos produced by a person, I believe his name is Dwayne Rich, DJ Rich, and goes by the moniker Mutual Information. He summarized the textbook you see on the left in those 6 videos and in 2 hours. And what I'm trying to do is now take those 2 hours and summarize that in about 20 minutes. We could start off with a Markov decision process. It's called Markov because if you look at the bottom of your screen, the probabilities we're thinking about have the Markov property. Looking in the future only depends on the present rather than further in the past. Overall, in kind of a game theory sense, as you can see in the diagram, we have to contend with agents and environment. And the quantities we're going to keep track of is if we're in a state S, if we're employing action A, and the amount of reward R. This will take place over time steps. And the probability at the bottom of the screen represents a distribution of probabilities of going to the next state and achieving a reward R, given the current state and the action that we're choosing. This is once again called the Markov decision process. In some more terminology, we have a policy P, or sorry, policy pi. Pi, Greek letter, corresponds to English letter P, but P was already used for probability, so we're using pi for policy. We could think of these trajectories of actions going up to a finite capital time T, capital T, and we could think of in the second bullet point, the returns or gains as all the possible rewards that we could get from now till the end. There may be some sort of diminishing marginal returns, though nearby rewards are more important than the rewards you may reap later on in the far future. If there is some sort of diminishing marginal returns, we have a penalty operator gamma that applies exponentially. At least conceptually, what we want is to somehow choose a policy of how to choose actions over the states. And of course, we want to maximize the expected return. In more statistical language, we're maximizing over all policies the expected gains. We have about 10 more slides, but plenty of time. So if there are any questions at any point, feel free to let me know. When you dig deeper into the formulation of reinforcement learning as far as the theory is concerned, we have a couple of different quantities to keep track of. The state value function, V, and the action value function, Q. You'll notice that V is a function of the states, and that's the expected gains from being in the current state S. Whereas the action value function Q is a function of both states and actions. It's the expected gains from the current state S and taking action A. What happens though is that as you go and take many more iterations, these equations tend to be coupled together. They tend to be related to each other, and you're going over many different time steps for T. So what started to make this study into the game theory and the reinforcement learning more rigorous was that it's now all connected by what are called the Bellman equations. If we're really trying to get a sense of the value of being in the current state S, we want to get a sense of adding up all the rewards that we could possibly take based on any future decision, really. So the expected value of being in the current state is the summation over all actions of the choices that we could take from here. But then in the third line, the action state equation says that its expected gains also depend on the state and the actions. But what is more important here is to note that what the Bellman equations allow us to do in the computations is that we could connect all the state values. Namely, if we have the values for some of the possible states in a scenario, we could use those to solve for all the other ones. And that makes something feasible for computation's sake. perhaps again, thinking more on the theoretical side of things, we want to get a sense of what optimal means in the Bellman equation formulations. We hope that there is an optimal state. Let me get the optimal state value function and an optimal action value function. These are denoted V star and Q star. The optimal state value function, the top equation, would simply be the maximum action that you can take. What's the best action you could take right now? This is in the guise of for all states available and for all actions available. Now, and especially when you're thinking of this in the Markov property where you're only thinking about one step at a time, if you're thinking about choosing the best action right now, this is sometimes called a greedy algorithm, that you're only choosing the best number at the moment, which may be good, may be bad, depending on the situation. For the second equation, the action value function, the optimal one's denoted Q star, and as you can see is the summation of the probabilities of going to the next state times the values that you would get from the next state and the rewards that you could reap. Now, part of the reason that this is a theoretical construct is this part here in the middle, we don't actually know the probabilities in advance, and especially in complex situations. And when we don't know the posterior probabilities, that's when we need to employ Monte Carlo methods. In order to get our MC-MC chains, we generate samples, which at least here in the early goings are usually in an order like this. We're at an initial state knot, taking an action knot, getting reward 1. We move on to state 1, employ action 1, getting reward 2, and so forth. These are simulations in MC-MC, and they might not be going through more of a theoretical construct. We acknowledge that the averages we get, we are hoping that they approximate the expected values for our situation. And admittedly, for the sake of time, I want to mention that there is a notion of generalized policy iteration. That is, your choices of actions to take should improve in wisdom iteratively. It's in my opinion, a fairly complex topic to talk about, generalized policy iteration. You're literally iterating and improving the policy. So for the Monte Carlo methods, we want to approximate the state value function over a policy, and that's the expected gains over, say, 10,000 MC-MC chains. So that middle equation simply says we take about 10,000 chains, ask which ones happen to have gone through this particular state S, and take the average of the rewards, the gains for that state. When we're updating the state values, we have a step size alpha, which will be multiplied to the difference between the gains and the previous known values for that state or assumed values. In various iterative procedures, you kind of get a sense that with the step size, you sometimes maybe want a small step size to be perhaps cautious or conservative. Or sometimes you may want a larger step size to go through the feasible space more aggressively, but it might not converge as well. The YouTube presenter wanted to emphasize at this point that we have a trade-off, namely the exploitation trade-off. If we want to discover optimal policies, we must explore all the state action pairs. But if we want to get high returns, we must exploit known high value pairs. And especially later on, if you don't have a finite space and you're only talking about samples of some sort of larger space, you might not be able to achieve both of these goals. So this constitutes one of the trade-offs you find in machine learning. We, in the past, mentioned the bias variance trade-off. And in computer programming in general, you might also have a speed versus complexity trade-off. There are these issues you must think about. And at some point, I need to fix this typo later. Admittedly, for the sake of time, this session ourselves is 1 hour. It's tough to balance practical examples with the theory. The YouTuber Mutual Information spent a bit of time talking about playing the game of blackjack. For a quick refresher on that, for people who haven't played this in a while, blackjack is a card game. You get a couple of cards at first. They have various number values. They're represented on the vertical axis of the graphs. There's an adversary, a dealer, who also gets a couple of cards, and you only get to see one of their cards, which may or may not be an ace. That's the top of the screen. You, the player, have a strategy whether or not to hit, literally gain another card, or just stay with the number of cards you have. Your goal is to try to achieve a point total that's 21, but not more, or perhaps just getting relatively close to 21, and trying to beat the score that the dealer achieves. The notions that we've covered so far could play this game and give you a state space of probabilities that you could see there in these grids. Now, to get a sense of the feasibility of computing something like this in a relatively simple game, this particular programmer ran his code for 10 million games of blackjack. Oh, and to emphasize, this was using an MC method to play this game. Now, from there, what made reinforcement learning more prominent is that at some point you need to get rid of the Markov assumption. You need to have artificial intelligence that could go and look at more than one step backwards, that could actually take in more information and use that for its learning. When we talk about that, we are entering a realm called temporal difference learning. Part of its framework is it focuses more on what's called the Markov reward process, which is kind of similar to what I started this particular chapter with, the Markov decision process, but only talking about the rewards and not the actions, which probably makes more sense if I actually read the 300-page textbook. One of the issues that programmers wanted to address at the time is that making an MC chain, which could be pretty long, especially in our earlier discussions about, say, RNA and genomes, an MC chain could be pretty long. and it requires a whole trajectory or episode to complete before updating some of the probabilities thereof. And the programmers wanted these updates to happen a little bit more aggressively, especially to speed up convergence of their algorithms. So we replaced the gains measurement and actually look, in addition to once the next reward, looking at all the possible rewards that we could get in the future, maybe with some sort of diminishing returns as well. At least going n steps in the future, which could be more than one step, that is. And what happens is that the updates are applied during the episodes, whoops, another typo there, with an n step delay. Compared to the earlier Monte Carlo methods, temporal differences has some advantages, including that you could do some batch training, useful if you have multiple CPUs, maybe some parallelization as well. Eventually, when you're talking about the state value functions V, they don't actually depend on the step size nearly as much. It's not as important what you choose your step size to be. And the mindset was we're trying to maximize the likelihood coming from the Markov reward process, which may make more sense when you're trying to think about your objectives and how you're setting up these problems in the first place, rather than minimizing the mean squared error, which is the kind of the old-fashioned mathematical sense in the Markov chain formulations. From there, you might have heard a buzzword called Q-learning. What Q-learning does is it updates some of the state values each chunk Q after a Sarsa tuple, after several delays, but it does not have to wait for the entire chain to finish. Now, where that term Sarsa came in was kind of cute. When you think about the formulation for the learning of it all, states, actions, rewards, where Sarsa came from is that first bullet point there. When we tend to write out these equations, the letter Sarsa tends to come up quite often. So the people who investigated this decided just to name a group of terms Sarsa. And then from there, a group of these Sarsas is called a Q. You once again want to maximize what you're doing across all actions, but perhaps over several steps. For example, if you're a chess player, you might want to think 2 or 3 moves in advance. All right, so that was the first 4 of the 6 YouTube videos. From there, we realized that not everything can be written as a nice table. Not every game and its choices can be written this way in a tabular sense. So, for example, if you are trying to generate pictures, for example, and you say that your state space is all the pictures of cats and dogs, there are functionally theoretical infinite amount of data that could possibly be out there or possibly be generated. So we rhetorically ask ourselves, without infinite data, how can we still generalize? And quite frankly, how can we still get results that we find are still reasonable? Some of the internal theory in mathematics is called function approximation, which is bringing together supervised learning and reinforcement learning. We have, in theory, our state value functions over some policy pi. We're just going to have to approximate it with a finite number of parameters, a finite parameter space. Part of the issue is that in previous algorithms, we only updated the states that we visited based on some of the calculations we could do thanks to the Bellman equations. However, if you think of a linear combination, such as linear regression, and if you update the parameters, it will update many predictions. It will update many values for S. So a little change in W could affect many things in your formulation. As a theoretical construct, we have our value error. We have a distribution of states. We have the state value function over a policy. And we have our projection, our prediction for the state values over our parameter space. And our value error is over all the states, the sum of squared errors, what would we get? The issue, once again, is that we don't know this distribution of states. It's kind of a theoretical construct at the beginning, so we need to somehow approach that without knowing what it is in advance. And this is a situation you probably heard about before called stochastic gradient descent. We have a difference between the target and our current projection. We have a learning rate alpha, and we progress based on the gradient, the derivatives with respect to our parameters W going through the state space. However, when we think about minimizing a function, especially when they are more complicated in many more dimensions, when we think about that target selection, we do have the issues that come up, and you may have seen in your other classes. We may have multiple local minima. We don't know in advance where the global minimum is. So that's something we have to contend with. When we think about the statistical estimates and are they pointing us towards what we wanted them to point us towards, we actually might have biased estimation rather than unbiased estimation. So instead of just stochastic gradient descent, what people have been moving on in recent years, say in the past 7 years, is a slightly more complex notion, and that takes a compromise between various constructions, mathematical constructions, and that's called the semi-gradient temporal difference. And that will hopefully address some of these problems that may arise along the way. Well, I don't know about you all, but that felt like quite a bit. Once again, that's the end of this chapter. And if there are any discussions, please let me know. Let us know.
Thank you, Darren.
Thanks, Dirk.
Good.
Yeah, I was going to ask, should we try to actually understand the mathematical formulas or just the concepts? I mean, I guess my curiosity is about the importance of these concepts for future chapters. Do we have to understand the mathematical equations or just understand the concepts?
I mean, I agree with you that everyone makes a choice of how deep they want to learn this pun
Yeah.
intended. The Python codes tend to be pretty similar once you get into it, but in order to understand what you're doing, at some point you kind of want a sense of what gradient is. You want a sense of what step sizes are, learning rates are, and that's another level down. Going from there, if you actually want to understand what all the random variables are, the capital letters, I'm not quite sure what you yourself would need, or if we as a group need to do that either. So that's where I guess we're arguing with ourselves about.
Do you know if the current models that we have, AI models that we have, primarily employ temporal difference or Carlo or the MCMC approach? You talked about that and also you said QZ, was it what you called it?
Yes, Q learning.
Yes. So the current models that we have, do you know if which of this methods they employ, or how does that work in practice?
So MCMC became feasible about 12 years ago. Temporal difference or Q learning, I would estimate about 7 years ago, and temporal difference, I think, is still the current. I mean, those YouTube videos I'm referring to are 2 years old, so that's where we're at right now.
Okay.
And if you like those YouTube videos, that particular author has the code online. Each of those algorithms is about 100 lines of Python for whoever wants to dive deeper into that.
And I guess we're gonna see those concepts again, because like the handbook says, I don't know, for instance, in the beginning of chapter 5, when it talks about reinforcement learning, it says we're gonna look at the fine-tuning methods in section 4. That's like some chapters away. So I guess we're gonna keep like finding these concepts, and hopefully it will be like more like how to use them, and how the algorithms and the LLMs and everything, how they apply them. I guess it's gonna become like clear.
I think for my learning, I think I might need to spend some time kind of like actually playing around with these algorithms in Python or R to kind of understand. Because for me, I don't have like a super strong statistical background. So when I see like a bunch of equations on the screen, I try to understand like some of the coefficients, but I don't like I'm usually not able to get the whole equation and understand kind of like what's going on. But that also gets the problem like this, the handbook is like 53 chapters. So obviously if we did like just like 1 or 2 chapters a week, it would take pretty long to get to finishing it. So yeah, I wonder if there's maybe like some sort of compromise where maybe certain chapters could be selected and some could be taken for like a deeper dive than others, in a more practical way. Because I think it might be like worth some time just thinking about how to kind of go through the handbook moving forward if it's working for everyone.
Yeah, that might be the adaptive nature of it all. Whoever volunteers for a week, they don't have to do 3 chapters. If they want to do 1 or 2, that's fine as well.
The PowerPoint slides, I just signed up for some of the chapters. How do we do those slides in PowerPoint? How does that work? Could you expand a little bit more on how to generate the slides for this particular presentation?
There are a fair number of instructions on the GitHub repo, which the link is somewhere back in our Slack channel. Basically, you fork the repo to your computer, your RStudio session, type in some markdown to it, and then do a GitHub push back to the repository where the moderator will hopefully approve of your work.
I see. So I fork the GenAI repo.
Yes.
Okay.
So if a presenter wanted to spend just one session going over one chapter, how would that be handled? Like, because I noticed there like the dates are already kind of filled in for the date column in the volunteer sheet.
We're figuring this out as we go along. Just was keep communicating with each other in the Slack channel. I just before this hour finally just figured out how to change the dates in that Google Sheet, so I could do that. But otherwise, we are quite at time now, and I imagine folks do have somewhere to be. It was good seeing you all, and I will look forward to seeing you again next week.
Thank you. Bye.
Thank
Yeah,
you.
thanks, Garrett, for presenting.
Mhm.